Hello friends, welcome to the ATC Double Cut. I am Michael Woods, and today I'm going to talk about shade and photosynthetically active radiation, and specifically about the effect of clouds on shade. Now, this is something that I have written about on my blog quite a bit, especially about 2014, 2015, 2016. I've got a lot of posts from that era where I was making a lot of these types of calculations. So you can certainly read about this if it's something that you find interesting. And I think it's something that is really useful to be an expert about because there aren't a lot of tricks to grow grass in shade. Basically, like, you either have enough light or you don't. And so when you don't have enough light, I think if you understand what the measurements are of light, and you understand the quantities of light that are reaching the turf in the shade, and then that's not enough to produce good turf, and you know how much light you would require to have good turf, if you can understand those numbers, you can then quantify that and then communicate about it better to people that might allow you to change the grass or remove the source of shade, or otherwise solve the problem. But not enough light is kind of a unsolvable problem if you don't understand about the numbers. So this is one that if you deal with shade, I would encourage you to become familiar with this. So the post that I'm going to talk about today has a title of Shade Effect of Clouds. And this is one that I wrote earlier in June, and it was after I had spent a day in Tokyo that was very cloudy. I will put a direct link to this post, the post with the title Shade Effect of Clouds. I will put a direct link to this post in the show notes and in the video description, and I will encourage you to check out the footnotes of this. In fact, I may click through to those and show you what you can find in these particular links that I put in the footnotes, because there are a couple of apps there that allow you to get the photosynthetically active radiation numbers for wherever you are in the world, which can be kind of useful. All right. So this post was inspired by me spending an entire day in Tokyo. I had had a seminar about OM246 total organic material testing near Osaka on the previous day. And I took the bullet train over to Tokyo, and I was going to have some meetings and then go to a Yakult Swallows baseball game playing against the SoftBank Hawks at Meiji Jingu Stadium in the evening. And I was at my hotel in the morning, and I noticed, man, it's really low clouds today. It's very cloudy, but it wasn't really raining. Apparently, it rained 3.5 millimeters during the day. I looked that up. Yeah, at Tokyo, it rained 3.5 millimeters, which is not very much. It's just over 1/8 of an inch. But mostly it was just a very cloudy day. And I walked out to one of my favorite restaurants and had a leisurely lunch and took some notes. I had a great meal, enjoyed the view, and also I enjoyed the view of the clouds. And I thought, let me think, if it stays cloudy all day, I'm going to look up what the DLI was today, what the daily light integral, what the photosynthetically active radiation was at this location in Tokyo. I'm going to look up what that was compared to what it could have been, because I also realized this was on June 14th, this particular day, and I knew that that's one of the longest days of the year. So if it would have been sunny, then on one of the longest days of the year, there would have been a lot of photosynthetically active radiation. So I thought this could be a good example to show the effect of clouds on photosynthetically active radiation. And then when I went to the baseball game that night, it started off before sunset because the days are a little bit longer in June than they are in other times of the year. So the game was starting and it wasn't full darkness outside, so you could still see the light on the clouds. And I put a picture of that in the post, and there are very low clouds over Tokyo on that day, very low clouds over the baseball stadium. This is one of the oldest baseball stadiums in Japan, and it's pretty cool. If you haven't been to the Meiji Jingu Stadium, or you don't really follow Japanese baseball, you may not be aware that this is one of the few baseball stadiums anywhere in the world that still exist where Babe Ruth played. Now, Babe Ruth is a famous American player who played in the late teens and 1920s and 1930s. And in 1934, he made a trip to Japan with some other American players. Maybe it was like an American all-star team against a Japanese all-star team, and they played some baseball exhibition games. And he played a number of games there and hit a number of home runs at this stadium. So it was cool to go to that stadium. That was my first game at the Meiji Jingu Stadium, and I was thinking, okay, it's going to be cool to make a blog post about that and show these clouds and make some calculations for what the light was. On this trip to Japan, Babe Ruth also played golf at Tokyo Golf Club. There's a really interesting book by Joseph Grew, who was the American ambassador to Japan prior to and up to the start of World War II. And I believe that book is called 10 Years in Japan. And it is a surprising book because it's not only about diplomacy. There is a surprising amount of golf in that book. And Grew. It's is it Joseph Grew? I believe the name was. Yeah, I think it's Grew. So he was a keen golfer, and many people in Japan who he socialized with in the 1930s were keen golfers. And when Babe Ruth came on this baseball tour, he actually went to play golf with Grew at Tokyo Golf Club. I've got a blog post about that also, so if you search the ATC website for Babe Ruth, you will. I think that's the only post that that talks about Babe Ruth, and so you can read about that. And there's actually a video of that somewhere in an archive where you can watch that online now and watch him making a few swings at the old Tokyo Golf Club. That particular location is no longer Tokyo Golf Club, and the club still exists, but at a new location. Okay, that was a long introduction and a bit of baseball there, and a photo of very low clouds over a famous baseball stadium in Japan. So, June 14th, it's one of the longest days in the year in the Northern Hemisphere, and I checked and found that at Tokyo's latitude, the DLI, which is daily light integral, or the total amount of photosynthetically active radiation that you would expect at that location on a perfectly clear day, that would be 63.7 moles per square meter. And that is about what you get in many parts of the world on sunny days in the summer. In the winter, it might be half that. It really depends how far you are from the equator. Places around the equator could have the potential to have something close to 60 moles per square meter per day, pretty much any time of year. It doesn't vary much because the day lengths don't vary much when you're close to the equator. But as you move farther away from the equator and you have your longer days in the summer and shorter days in the winter, then the potential DLI that you could get on sunny days would change quite a bit depending on how long the days are. And so that's the maximum possible, 63.7. What the DLI actually was, and I looked this up because there is a sensor in Tokyo that measures the surface irradiance, the direct light from the sun that reaches the surface of the ground in Tokyo. And so from that you can calculate what the DLI was. The DLI will be about it's different units, but if you multiply that number times 2.04, or basically just double it, you will have in photosynthetic units the daily light integral. So the DLI actually in Tokyo was 16.6. So it was 26% of what it could have been. So basically that is 75% shade, basically. And that correlates very well with my rule of thumb about how to guess how much shade you are dealing with. I've got another blog post about that. I'm not going to talk about it today, but I will explain the story behind it, or just what this rule of thumb is. If it's full sun and you've got bright sun and it's full sun and the sun is not restricted by clouds, then you can expect you are in 100% full sun, right? That makes sense. But it's the degree of shade. How much shade are we dealing with because of clouds? And that one, if you have a sensor, which not so many people do, if you have a sensor, you can measure that. But you can also check, and you can basically check your shadows and check the sun position and figure out about what it would be. Now, how does that work? Well, if you can find that the sun is restricted by clouds, the sun is behind clouds, but you can still see where the sun is, and you can still see your shadow. So there's still a shadow on the ground. It may not be as distinct of a shadow as what you would have in full sun, but you can still see your shadow on the ground. That's going to be about 25% light restriction, or 25% shade caused by the cloud. If you can no longer see your shadow on the ground, you can't make out that you have a shadow, but if you look up in the sky, you can still see the location of the sun. You can still see that the sun is in this portion of the sky, or the sun is in that portion of the sky. If you can still see the direction in the sky where the sun is, but the light is so restricted that you can't see your shadow, that will generally be about 50% shade. That's blocking about 50% of the light. And then when you get really heavy clouds like this, when you get the clouds that are so heavy that they're noticeable like this, now you won't see your shadow. And if you look up and you look into the sky, you can't tell what direction the sun is. So you can't find the sun in the sky anymore because it is so much light is blocked by clouds. So now you're not seeing your shadow. You can't tell where the sun is. In that case, that will tend to be about 75% shade. About 3/4 of the light is blocked and not reaching the turf. And then at nighttime, when it's dark, that is nothing. Your light is zero. So that's pretty easy. And I suppose you could use that under trees also, although generally I find under trees it's usually about 80 or 90% light restriction. But it really depends on the type of tree and the type of canopy that you're dealing with. But when you're just considering clouds, I like to easily estimate what the light restriction is by just simply looking at 25% light restriction when you can see your shadow, 50% light restriction when you can no longer see your shadow, 75% light restriction or 75% shade, when you not only can't see your shadow, but you can also no longer find the sun in the sky. So that's a rule of thumb. And you might be thinking, well, Micah, that's fine, but how do I know what to compare it against? What could my maximum DLI be? What could be my maximum photosynthetically active radiation be? And that's where the footnotes, the links that I put in the footnotes of this post, might be useful for you. The first one, and I will click through to this, this is a PPFD by time app. So this is another one of the shiny apps or calculators that it's using a server running R software in the background, so it can make a lot of calculations that are relatively easy, or the calculations are straightforward to make in R, because R is a good language for doing data analysis and calculations, and it happens to be one that I know how to make these calculations in. This shiny app is making calculations using the R language. And this one I call a PPFD by time. PPFD is the instantaneous light, the instantaneous photosynthetically active radiation, and that is measured in micromoles of photons per square meter per second. And then if you add those up over the course of a day, that becomes the daily light integral. And so you either look at the photosynthetically active radiation that's instantaneous, or you look at it in total. And you'd use these for two different purposes. If it's 9 a.m. and I want to know how much shade a particular building or hill or clouds or tree or hedge or fence, if I want to know what the light restriction is at that particular time of day, then I can go into a sunny area. You can calculate this by comparing the sunny area to the shaded area. So let's say I've got a lawn and it's got a fence on it, and that fence is throwing some shade on the turf. I can go measure the instantaneous photosynthetically active radiation, which is the PPFD, the photosynthetic photon flux density. I can go measure that with a meter in full sun, and I can then go measure it with a meter in shade, and I can tell what the difference is, and that's going to give you the degree of shade that you have. But if you don't have a meter, then there's some other ways to do this, and one way is just to know that in full sun, you're going to expect that about 75% of the light that reaches the top of the atmosphere above your location, about 75% of that light is going to make its way all the way to the surface. So if you know the latitude and longitude point where you are, then for that particular square meter, you can go up to the top of the Earth's atmosphere, and there is a relatively constant amount of light coming from the sun at a particular time of day, at a particular latitude and longitude, and on a particular day of the year at the top of the atmosphere. And then if it's sunny, if there's no clouds, you can expect 75% transmittance of that light down to the surface. And there are some calculations involved, but that's why you use a calculator like this. So this one, I'm gonna update it sometime. In fact, I made some calculations today that I think will allow me to make this much simpler. So the first thing we do is look at the date. I'm recording this on June 24th, so it starts off with June 24th. Let's go back to June 14th, that day that I was in Tokyo. So I'll select June 14th, and then the hour, let's select 9 in the morning and 16 minutes after the hour. And I've set it for Bangkok's latitude. Let's go up to Tokyo, which is going to be about 35.7 or something. All right, so that's all straightforward. the day of the year, the date, the time of the day that you want to check what this would be in full sun. So that's, here I've selected 9 hours and 16 minutes, or 9:16 in the morning. And I've selected the latitude for the location that I want to check, and that is my memory telling me what Tokyo is. So that's pretty simple. But now the app is a little bit complicated because I copied the longitude instructions pretty much straight from the FAO 56 crop evapotranspiration guide, which is where I figured out how to make these calculations. And the way that they do the longitude is not just putting in your longitude point. They ask for two things. They ask for what your longitude is, not east or west of Greenwich. So if your longitude generally, if you go to Google Maps and you look at the way the longitudes are listed in the locations that you find on Google Maps, if you go to the west of Greenwich, you will have a negative longitude, and if you go to the east of Greenwich, you will have a positive longitude. And you do that until you get around to until you get to 180. So you'd be like 179.99 west, negative 179.99 west, and then it would stop, and you'd then be like 170. What is it? Yeah, 179.99 east. But that would be a positive number. So somewhere over the Pacific Ocean, it flips. So Bangkok is 100 degrees east, and that's a positive number, so it's 100 degrees east. And if you're in New York, I forget what it is. Maybe it's minus 70 or something. I think that, well, I mean, I believe that's how it works, is you go negative to the west of Greenwich and positive to the east. But that's not exactly what this app is asking for. So I find it's kind of unusable to get this correct, because you have to express your longitude in the degrees west of Greenwich. So a place like Bangkok that is basically 100 degrees east of Greenwich, if you express it in degrees west of Greenwich, it's about 260 degrees west of Greenwich. And that's not the way we ever think of it. But today I made some calculations for a different project I'm working on about evapotranspiration, and I realized that I can figure this out for you. So I could just ask you to put your longitude in, and I can make the calculations on my side for what the degrees are west of Greenwich. So you don't have to do it. So I am looking to update this app and just make it a little bit more easier to use, because the next requested piece of information is terribly complicated. And that is asking for the longitude at the center of the time zone in degrees west of Greenwich. And that basically is asking it's basically asking what time zone you're in, and then taking the number of time zones that you are west of Greenwich and multiplying it by 15. So that gives you that number. And these are necessary to calculate solar noon, and there's a lot of calculations involved to find out at your exact location how much light there is at the particular time of day that you're asking to get the information. So I'm going to guess what Tokyo would be. So the default values here are set for Bangkok. Bangkok, I think, is about another 30. So that's going to be, right now I've got it about 260, which is Bangkok. It'll be about 230. I'm going to be a couple degrees wrong there, but this will get us somewhere close to Tokyo. Longitude at the center of that time zone, that's 2 time zones away from Bangkok. So that should be we should go 30. So it should be 225 maybe. Anyway, you can if you're hearing me kind of stumble through this, or if you're watching me kind of guess at what these numbers should be, you can realize that this particular calculator has a nice opportunity for improvement by just saying, please input your longitude and let the calculator figure this out for you. So I wrote this app. When did I do this? I'm not going to click on that because that's going to lose what the code is on GitHub. So if you want to see these calculations, you can check out the code on GitHub. You can see when I made the commits on this. I think it was probably in 2015. So since then, it's been about 8 years of me continuing to work with R software and work with making Shiny apps and these types of online calculators and so on. I've learned how to make things a little bit easier. So I'm looking forward to updating this one. Anyway, you can also choose the transmittance. I generally use a transmittance of 0.75. But of course, if you have smoky skies or if you have more air pollution or something, you might have a slightly lower transmittance than that. But generally on clear skies, no air pollution, I'm going to assume that 75% of the light that reaches the top of the atmosphere is going to make it to the ground. And then there's like this magic calculation, because down at the bottom of the app, it says the expected ppfd in full sun at 9:16 a.m., 9:16 in the morning on June 14th is 1,506. Now remember, that's specific to this particular latitude and longitude point, which I'm approximating Tokyo here. And it says if there are no clouds on this day, the DLI at this location is expected to be 63.7. And remember, that's the same number, 63.7. That's the same number that I had for Tokyo, what it would have been on June 14th. So I guess I guessed my latitude pretty close. For your PPFD, which is the instantaneous photosynthetically active radiation, how much light you have this very second, for those numbers to be correct, you need to get the longitude information correct on here, because that's what's telling you, that's where it's figuring out what time it is, and it's figuring that out by the longitude. If you put your correct latitude in here, it doesn't matter about the longitude being correct. It's going to make your DLI. Your DLI is always going to be correct, I think, just based on getting the latitude. So if we just flip it around, let's go somewhere south of the equator. So now we'll put a negative latitude. Let's go negative 35. So this is on June 14th, which is going to be the start of winter in the southern hemisphere, or late autumn, and it's very short days. And at that location, the DLI is expected to be 24. Right, so we've gone from 35 degrees north latitude, which is about what Tokyo is. It's about what Raleigh, North Carolina is. When you're at that latitude in the summertime, you can expect the potential DLI on a sunny day is going to be a little bit above 60. And that's plenty of light. That's a lot of light. But you look at the shortest days of the year, so we can do that by just going to the southern hemisphere at 35 degrees south. Now the DLI is only going to be 24 if it's a sunny winter day. And we can go even farther south and the DLI should go down. So let's go to like the Antarctic Circle, which would be about 60, minus 60. So at that latitude, the DLI is expected to be 3.15. That's nothing. Let's go to the northern Arctic Circle on June 14th, and I'll put, so that's about 60, it's like 63, 64 degrees. I know those of you listening in Iceland or in Sweden or Finland or Norway, you can correct me about what the what the exact latitude of the Arctic Circle is. But if we go to 60 degrees north, then the DLI is expected to be about 63. And I'll just check at the equator. I like this app. I love these numbers. Yeah, so at the equator, the DLI maximum would be about 51.2. Maybe I misspoke. Let's go somewhere closer to like March. Yeah. So if we went to like March 14th and we were at the equator, the maximum DLI would be about 58. So anyway, these numbers change through the year, and this app, if you ever really want to get into this and make some calculations for your site, you can use this app as it is right now, and eventually I could even add like a download button to just say, okay, if you're at this latitude, it will generate what your full sun DLI would be for the entire year or something like that. But I haven't really promoted this app so much recently because even I struggle with these longitude degrees west of Greenwich, because normally you're dealing with east or west, just a single longitude number, and especially that longitude at the center of the time zone. But I think I made a breakthrough today to possibly be able to figure that out a little bit easier. So stay tuned. I'm going to show one more app. This one's a little bit more user-friendly, I think. Oh, I stopped sharing my screen. Let me start doing that. So I'll start sharing my screen, and I will bring it up on the screen. So now we've got a DLI Anywhere app. And this one, some of you will have used it before. This one lets you find the daily light integral at any location. And this is using satellite data for anywhere in the world. So we can go to, where should I go? Let's go to Tokyo, just because that was the place that I started talking about. And by now, June 14th is probably on that map. So, it's in the satellite data. So if we go on this up to Tokyo, what you have to do to use this app is click on a location and it'll form a little highlighted rectangle. So that's the area where the satellite data will be coming from, where we'll look at the DLI. So it's 35.7 north, 139.8 degrees east longitude. You click on the Get DLI Data, and that will get the past year of data. And then if you continue through this, you can click on what the normal monthly DLI is, so it's getting the normal data, and then it allows you to download the DLI chart. And that one I will download, and then maybe I will show that. Let's see. I want to put that. I'm not quite sure I know how to share that. So I'm going to go back to the start and get that data again and just show it right here in the browser. So I quite like this. You'll find it's formatted a little bit better when you actually download the file for your site. But if you're interested in this, this shows the entire past year. So it's showing the maximum DLI by the satellite data at Tokyo was on June 29th of 2022, and that value was 57.3. And it shows the minimum DLI was in November. On Wednesday, the 23rd of November, the minimum DLI was 2.8, which is not very much. And I add up all the weeks. So this app found that in the 50 to 60 DLI range, there was 1 week in the year that averaged at that level. And then there were 3 weeks in the year that averaged in the 40 to 50 level. So you can find this for your location, or you can check it for places that might be similar. And this is something that if you're dealing with light restriction issues, if you're dealing with shade issues, I would suggest becoming familiar with PPFD, becoming familiar with becoming familiar also with DLI, and know what it could possibly be at your site, and then figure out where you have the shade areas, figure out what the DLI or the PPFD actually is in those areas where you're dealing with shade problems, and then you'll be able to communicate better the magnitude of the problem and why things need to be changed. All right, that was kind of a technical one, but it's important because the light is something that is kind of out of the turfgrass manager's control, and it is governed by the time of year and by how much sunshine you have, and also by what structures or vegetation or mountain ranges or other things you may have that are blocking the light. So it's something that I didn't learn about this in school. Certainly not what I've talked about today. I didn't learn about in school. I'm self-taught on this. So I did this by continuing education, and I hope that you'll find it interesting enough to do some continuing education yourself about these particular topics, because light is critical. So you've got temperature and light are a couple things that really affect growth that are out of the turfgrass manager's control. So then some of your options, if you deal with terrible shade problems, are either like cut down the tree, bulldoze the building, move away from the mountain, change the type of fence that you have, change the type of roof that you have, or change the grass. But even if the shade is so severe, you can't just change the grass and guarantee that that's going to solve the problem. So you need to start looking at these numbers. What's the degree of light restriction that I have because of the shade, and what is the light requirement for the particular grass that I want to use? What type of temperatures do I have at this site? Could this grass even survive in these types of temperatures? That type of thing. So I often use this for my own work to look at how much of a shade problem we're dealing with, and I think you can probably use some of this yourself too. So in fact, both of those apps that I showed, both of those Shiny apps, which are in the footnotes of the blog post that I shared, you will those are apps that I developed because I was looking up that information myself on a regular basis for the types of information that I provide to people, and answering questions that people have about light. So I think that they're probably of interest to some other people out there and not only me. All right. Thank you so much for listening. It is time for me to sign off now. I am on the northern outskirts of Bangkok. It's a Saturday evening, and I'm fixing to go have a lovely meal somewhere and then start heading home. So I will sign off now for ATC from Nonthaburi, Thailand. I am Micah Woods.